In Module 5.1, we talked about how climate scientists put together estimates of previous climatic conditions. Now, let's see what they tell us. First, we can look at the direct temperature record for the last 150 years or so. We see a few things here. First, global temperature has increased by about a degree Celsius over that time, with a lot of the increase concentrated in recent years. It hasn't been a consistent increase. There was warming up through the 1940s, then a slight cooling into the 70s, and then warming since then. Even though the warming has only been about a degree or so, that's so much greater than the natural variability in climate that 1976 was actually the last year when temperatures have fallen below the mid-century mean. If we compare the temperature change to the atmospheric carbon levels, we see that the increase in carbon is much more consistent than the temperature increase, showing that CO2 levels aren't the only thing that affects surface temperature. But it's also true that if we took a naturally varying but stable surface temperature trend and superimposed it upon increased forcing from carbon, the shape of the curve that we see is pretty much what we'd expect to see. So the trend is certainly consistent with CO2 as a driver for the long-term trend. We can go back a couple thousand years relying on a multitude of proxies, including tree rings, corals, ice cores, boreholes, forams, written historical records, and so on. This reconstruction from the IPCC's fifth assessment report shows a fairly stable climate, but with some important trends. For example, about 1,000 years ago, we see temperatures that were maybe half a degree warmer than the long-term trend. We call this the medieval warm period, and it was the period when the Norse established permanent colonies in Greenland, for example, and British vineyards were able to grow grape varieties that had previously only been reliable on the continent. Then, around the 16th century, temperatures fell to something like half a degree below the long-term average. This period has come to be known as the Little Ice Age, and observational records from Europe suggested pretty significant local cooling. Globally, climate shifts within these parameters have been linked to the collapse of major civilizations, including the Maya in the Yucatan, ancestral Puebloans in the American Southwest, Angkor in Cambodia, and so on. But as fluctuations go, they were roughly half as large as our current one. Based upon our reconstructions, we can say with high confidence that the global climate today is warmer than it has been at any time in the last 2,000 years. Going back to about the last 10,000 years reduces our options for proxies. Forams, speleothems, plant microfossils, pollen, lake sediments, and ice cores are the most commonly used data sets in that range. Because the record in this time frame is spottier, we have fewer types of records, and some of our better proxies are no longer usable. So there's a lot more uncertainty as we go that far back. What we can say is that temperatures appear to have peaked around 8,000 years ago and have been generally getting cooler ever since. It appears likely that temperatures today are warmer than any time in the last 10,000 years, but our confidence in that statement is lower than it was for the last 2,000. In this class, I want you to keep 10,000 years in your mind because it's roughly the time when the planet emerged from the last ice age and marks the beginning of the most recent geological period known as the Holocene. The Holocene is really thought to be the most recent of a series of interglacial periods, but this one has been relatively stable and long-lived, and since it's the one in which civilization arose, we get to call it special. Many scientists argue that we've recently entered an even newer geologic age known as the Anthropocene, and we can talk about that in class if you feel like it. The Holocene is also the period when humans developed agriculture, almost immediately after the end of the Ice Age. It's fun to speculate that the stabilizing climate may have made settled agriculture possible, but it's not at all clear if that's true. If we want to go back farther than the Holocene, the picture changes dramatically. The epoch before the Holocene is called the Pleistocene and runs from about 2.6 million years ago until 11,700 when the Holocene began. The Pleistocene was the period in which the planet descended into a series of ice ages, as well as the time when Homo sapiens evolved. Again, our climate proxies become more limited, and much of what we know about the late Pleistocene climate comes from ice cores. We have cores from Greenland going back about 400,000 years and cores from East Antarctica going back over 800,000 years. If we study these cores, this one from Greenland, we see several things. First, temperatures fluctuated between cold glacial periods and warm interglacials. In Greenland, the difference between a glacial and interglacial is on the order of 10 degrees Celsius. Some of these transitions were extremely rapid. For example, as the planet came out of the last ice age, it went through a complex transition period, first warming, then abruptly cooling, then warming again. The cold period from about 12,900 to 11,700 years ago was called the Younger Dryas event, and is thought to be related to the shutdown in the currents that drive tropical water poleward in the North Atlantic Ocean. Transitions around the Younger Dryas event appear to have occurred over a span of several decades, and areas like Greenland saw average temperature change over 10 degrees Celsius in that time frame. Other regions also saw abrupt change. For example, what's now Venezuela saw temperatures change by about 3 degrees over that time period. On the other hand, temperature changes in Antarctica over this period appear to have been out of phase with Greenland, which would make sense if the cause were a shutdown in heat movement northward. All things considered, climate changes during this period appear to have been more abrupt than what we're experiencing today. We have to go back over 100,000 years before we get to the penultimate interglacial period, sometimes called the Eemian, though that depends on what part of the world you're looking at. It's fairly likely that temperatures were warmer during the Eemian than they are today, although I can't say that with much confidence because we don't have good global records. Still, that may be good news for our planet because the ice sheets didn't collapse during the Eemian, suggesting that they may be able to handle more warming. That said, the very warm period was fairly short-lived, so it's hard to know how good an analog it really is. You'll often hear people say things like, temperatures have never been this warm, or it's never changed as rapidly as it's changing today. Well, neither statement is strictly true. Careful people will say something like, never in the last 10,000 years, or never since the dawn of civilization have temperatures been this high or changed as rapidly as they're changing today. Those statements do appear to be true. If you go even further back, you can see cycles of warm and cold periods, and the correlation between carbon dioxide levels and temperatures is extremely close. It's not that one drives the other. At times carbon dioxide changes first, and at times temperatures change first. And in fact, gas bubbles can move very slowly in glacial ice, so the clarity in this figure in terms of what comes first is a little misleading. But if neither temperature nor carbon dioxide fully drive the other, what the data strongly suggest is that there are periods of strong positive feedback between them. In class, we'll talk about Milankovitch cycles, but for now, suffice it to say that what seems to be happening is that the timing and intensity of solar radiation hitting the northern hemisphere in the summer can trigger bouts of glaciation or melting, and then feedbacks, in particular through temperature effects on the biosphere and the resulting impact on carbon dioxide emissions or uptake, drive and then stabilize a new glacial or interglacial climate regime. One potential cause for concern is that we know that there are conditions under which temperatures are relatively stable and then conditions under which positive feedbacks kick in and the climate system rapidly changes state. It would be a rapid state change like we see during climatic transitions, where the climate sensitivity to small forcings is abruptly increased, that would lead to some of the doomsday scenarios that you sometimes read about on the web. Paleoclimate is a fascinating science, and I'd love to spend weeks talking about what we know about past climate changes and their impacts on the biosphere, but we'll end it there for now.